This section is called Change of Concentration with Time. And what it involves is the integrated rate law, where we now want to put time into the calculations we've learned about. We've learned about rate constant and we've learned about concentration. So when we talked about a reaction order, you can determine it by the method of initial rates, but it's not very good. It's very laborious. Instead, what we would like to do is take our data and in a graphic way, figure out what's going on. The whole idea behind this is we're going to fit our data to a straight line based on the reaction order, and it will be a line that follows y is equal to mx plus b. We also have another item to introduce. It's called the half-life, and that's the time that's required for the reactant concentration to decrease to 1/2 the initial value. Simply put, 10 goes to 5 in one half-life, 2.5 in another half-life, 1.25 in another half-life. So let's do the details. Zero order. We're going to talk about zero first and second. Now, you have a chemical equation. You really just think about the reactant. From the initial part of this chapter, we know that is the reaction for, or the rate law for, a zero order reaction. If we think of it in terms of calculus, we would be using the expression where we related the stoichiometry. Well, what we're going to do is we're going to combine these two equations. Here's one part, here's another part, and what I'm doing is combining them. Now, when I took chemistry, we had to do the derivation. No longer takes place. I'm just going to say integrate using calculus. Text is going to ignore this A. It will bother those of you that know calculus, including me. And what we're going to do is rearrange algebraically that equation so that it is a y is equal to mx plus b line. The slope of this line, the k, is minus the rate constant because k has to be positive. If I substitute in a0 and 1/2 a0 for a at time t, I will come up with this expression for the half-life, okay? Moving on into first order. Notice the reaction looks the same. The rate from the beginning of the chapter looks the same, but now the rate law, it is first order. Once again, I will combine those two equations and they will be integrated using calculus for you. Once again, your textbook is going to ignore A, and it will be rearranged for graphing so that y is equal to mx plus b. The slope remains minus k, but k must be positive, and here is our expression for the half-life. I rolled through it quickly because, again, this is the background behind what we're doing. What you will be having to do is deciding on an order. If someone gives you data, you need to find a straight line. What do I mean by that? Well, your textbook talks about this isomerization process, where here carbon is bonded to nitrogen and here carbon is bonded to carbon. What they want to do is say, if we take some data, if I measure the pressure versus time, which order am I looking at? So I wrote down the zero order, I wrote down the first order, and I plotted the data according to those integrated rate laws. The zero order is pressure versus time, and as you can see, it is a curve. So it is not zero order. We know that. If I look at the second set of data, I see this very, very nice straight line where its slope will be minus the rate constant. You can't be expected to plot data on an exam, but they could show you two different graphs and ask you which of these is correct. Really, the way to tell what's going on is the y-axis label, okay? And I mean that by saying, look back up here. Here we have concentration. Here we have log of concentration, ln of concentration on our y-axis. Now again, I always scratch my head. Why do we have pressure and not concentration? I don't know what your textbook authors were up to. What you will be expected to do on an exam is a word problem. And I learned from teaching online last semester, you really have to set things up. So let's read the problem together. It says it follows this rate law. Since there's the number 1 here, I know this is first order. Let's list all the things they've told us. They told us that the K is equal to 0.00840 seconds minus 1. They've told us 2.5 moles in a 5-liter container, 2.50 moles in 5.00 liters. That is going to give me a concentration of 0.500 molar, and that will be what we would call our concentration A0. Then they tell us the time we want is 1.00 minute. So I would suggest always list your data. It helps you get along. ln of A, we don't know what that is. K, we have been given. Time, we have been given. ln A0, we have been given. So again, learning from last semester, type it up before you get started. We know that our time is 1 minute, and it's 0.00840 per second. 60 seconds in 1 minute, we get a mathematical number. ln of 0.500, a mathematical number. Take those two numbers, combine them together. How do I clear an ln? Well, I raise whatever it is to the e power. So I have my N2O5 equal to e to the minus 1.197. I come up with 0.302 molar. So I've crunched my things through, but what I didn't do is to say how many moles of N2O5. I have been given here molarity, 0.302 moles per liter, and my amount is 5.00 liter. It tells me that 1.51 moles of N2O5 remain. Yeah, the expectation's pretty high here, but this is Chemistry 1220. So this is a word problem that is based on a first order process. We could have had graphical numbers, can't do on an exam, but you can do something like this. Finally, there is a zero order, there is a first order, and also there is a second order. We can't tell from the chemical equation, and here again is the expression that we learned in the beginning of the chapter. Here is the rate law for a second order. There is the number 2, all right? So essentially what we have here is we're still going to combine these two equations. We will use calculus to integrate them. We again will have the text ignoring the A, and we will rearrange it for graphing. What is the change? Well, now my y is going to be 1 over the concentration of AT. My slope is now positive, so that's a K, and my intercept on the b-axis is 1 over A0. So I noted these things down here, as well as the equation for the half-life. And the half-life, again, is how long for half of the concentration to disappear. You no longer have to do the calculus derivation like I did learning this. You do have to know how to do a word problem or recognize it from the data. In part 2, we'll talk about what the second order process looks like.